Yeah, it's like, what's it like? Anything will let you.
There's several like ways to sharp LabVIEW. Like a C-sharp API.
Doing a sound check. You can just hit the chat and say, yes, I can hear you, if you can hear me.
I'm trying to do the same thing right now. Yeah, I know that have a lot of friction. Not that you didn't. Move that over. Running into all sorts of weird issues. Process running. Spell and t-shirt. The only reason I thought of that is where new. Having trouble once. Like, oh, we're talking to you now.
I can hear you.
I don't need to end until, sunrise. No, they drag streets through Thursday after parties. Awful. The streets got clear. Yeah, that's true. Why would you, Didn't even occur to me. I don't know. You only need to do that once in life.
All right.
We should be good.
All right, cool. Then I think we'll go ahead and get started as it is, 6:14. Good evening, everybody. Welcome for joining us at tonight's LabVIEW Architects Forum. I'm Smith. I'm playing the part of Fabiola tonight, as she had to be somewhere else. So I'm going to facilitate tonight's meeting, introduce our speakers, etc., etc. I don't think we have any business to discuss, so I think we'll just get right to it. We have two presenters tonight. Both of them, a word from our sponsors. Booth tonight is courtesy of National Instruments. And again, the room, we thank NI for giving us a place to have this meeting. And it turns out that both of our presenters tonight are NI employees as well. It's supposed to be a user-run meeting, really, I promise. Anyway,
Any new people?
do we have any new people? Anybody who hasn't been to one of these before? Okay. The guy who sits in my queue. Do we want to have the new people introduce themselves? Yeah, go ahead. Start with Craig. Introduce yourself. Tell us about yourself.
Craig Hitchman.
Hi, Craig.
Hi, Craig.
I recently joined the system engineering group at Nagle, so I've been bugging him. Pretty fun.
How many years have you been in LabVIEW?
3, maybe a little bit more. Not super long.
He's a fast study, though.
He is. Who's next?
Hi, I'm Xavier. I recently joined the AES group, and I've been using LabVIEW, I guess, for about 2 years.
Cool. Welcome.
So AES is Applications Engineering Specialist. I'm on the RF wireless.
Hi everyone, my name is Sunday. Similar to David or Xavier, I am on the AES as well, and especially files.
Cool.
All right, just a note. I'm listening in here. I'm muted so they can't hear me. But if you're communicating, project your voice if you're in the back or so, and we can reflect questions up there. Remember to do so. That way, everybody else can hear.
Okay. I don't know about repeating the bios.
You can talk louder.
I'm Jeff Lambert. I'm an RF test engineer in the test engineering for about 5 years.
Oh, cool, awesome, welcome. This meeting was originally intended to be for the local user community, but because of our proximity to NI, we usually have a very healthy NI presence as well, which is pretty awesome for cross-pollination of ideas. Anyway, so tonight we have two speakers. Jim Nagle is going to present on getting the most from LabVIEW curve fitting, and then we'll take a break. And then after the break, we'll come back and Norm Kirchner will present on Pacifying the Newborn, top-level baseline prime and its infancy. So without further ado, give it up for Jim Nagle.
Good evening. So my name is Jim Nagle. On the forums, I'm DSPGuy. The idea for the presentation kind of came about from a couple of replies, postings that I noticed. I tend to reply mainly to the optimization and curve fitting type questions. So not a lot of posts, but in that particular niche, it seemed like there was a fair bit of what I was thinking was a lot of numeric issues. And after seeing some things over a couple of years, I thought it might be interesting to present on some of these use cases. Rather than, say, do a top-down presentation where, say, okay, do this, and here's an example of doing this. Let's go ahead and throw some problems from the forum up, take a look at how we address them, and then maybe get some best practices in a kind of bottom-up fashion. So without these four, in particular, the first one, Christian Altenbach, he's a real rock when it comes to supporting curve fitting. He was invaluable in providing feedback in version 8.0, and we actually changed the implementation and interface for curve fitting. So my thanks to Christian and Darren, Johnzold, and Ravenspan all consistently post replies. Darren has excellent math capabilities. He's constantly being very particular and correct in his responses. So my thanks to everyone. So the three categories, I started to look through the posts that I had gathered together. I noticed that they kind of fell in three categories. One was modeling. So kind of how can I fit this kind of model? It doesn't exactly work with the interface that we have in LabVIEW. Second one, numeric. So my initial guess coefficients are unchanged at the end of my curve fitting. Something went wrong. How can I fix that? And then the third one is performance. Now the numeric and performance are the ones that I was most interested in, and I kind of had it in my head that these are the ones that stuck with me, that these would end up being the majority of problems. But when I went back, and I think I had something close to 300 bookmarks, and I just started browsing through them, culled them down to a subset, and then from those I picked what I was going to present tonight. The vast majority ended up being modeling questions. And it was kind of a surprise. It was a good thing that I looked at it, and I'll get this feedback to the right people, but it was interesting. So the interfaces, I don't really want to cover how to do curve fitting from a beginning standpoint. My assumption is that everyone knows how to use the VIs, and that we're going to cover particular cases and problems. So I'm not going to look at the express interface. I'm not going to look at the formula string interface. It's going to be the VI reference interface for nonlinear curve fitting, the constrained version of that, and general linear fit. Please feel free to interrupt at any time if you have any questions. So let's get started. The first post I wanted to take a look at, there was a question about lemma fitting, and by the way, I mean no disrespect. Throwing up people's questions here and then kind of picking it apart and whatnot. It is out on the forums, but I may show something that could be done differently, but I don't mean to put anyone in particular on the spot for what they put on the forum. So in this case, the problem was that there was premature convergence and poor fit. This is what the original poster had complained about. The model was in this form. The orange coefficients are the actual coefficients of the model. T is the range, L, A, W are the domain of the function. So these three terms are linear in these particular domains, but the hyperbolic tangent makes it nonlinear, so it ends up being a LabVIEW type problem. So let's take a look at it. If I take a run this application, what we're looking at in the graph is just the original data is in white, the best fit curve is in red. I didn't blow the, I guess this is pretty visible the way it is. The problem is the residue is pretty large. I don't know this application, and the original poster didn't explain this very much. When you have lots of domains, it becomes kind of difficult to understand what's meant. So the residue is the total squared distance between the best fit curve and the original data.
When you say total, you mean sum?
Yeah. And the number of function calls here is relatively low for LabVIEW. It's 10. So it kind of indicates that the initial guess, the initial parameters are here. Best fit parameters, there is some deviation here, but the fit seems pretty bad. In other words, the red doesn't really resemble the white as you would hope if that was a good model. So if we take a look at this, after much cleaning up, the code looks something like this. So here we have the domain and range, values coming in. Here's the LabVIEW fit VI. Nothing jumps out here. So one of the things that is useful to do in fitting, and when you don't know how to get started, is to start verifying or validating your assumptions. And the primary assumption is, did I get my model right? Did I implement my VI right? Did I pass the reference in the way I expected? So this is the model VI. Now, I can look at this, and again, I don't understand the original poster's application very well. I can look through this and try and verify, well, back out the formula and figure out, did he get the formula value correct here, and are the partial derivatives correct that are being output here? But it's pretty tough to do. So rather than doing that, a useful exercise is to take the model, and these three arrays here are the domains. So I'm going to pass the domain into a call by ref. So I'm going to call my model function that I wrote using call by ref. I'm going to pass in the domains, and I'm going to ignore the range. I'm going to ignore the data that was part of the problem, and I'm just going to generate my own range value. So I'm going to use the initial guess. I'm going to pass that into the model function, evaluate it over the domains, and then I'm going to take the initial guess and perturb it slightly. I'm just going to subtract 0.01 from each of those values. The idea being that I'm close to the solution of the problem. I should be able to run LabVIEW with that model and that known starting point, and I should be able to recover exactly my initial guesses. So I'm not adding any noise. So it's just a way to validate, hey, I've got things working the way they should be. Does that make sense? So if I take a look at the best fit parameters that come out of that little exercise, I expect to be able to recover these values exactly. And you can see that I don't. So it indicates that there is something wrong with the model function. So if we take a look at the model function again, one of the easiest things to do to actually get wrong is to get either the computation of the partial derivatives wrong, or to get the ordering, the column or row swapped, or have some kind of problem. LabMAR allows you to specify the partial derivatives directly. If you don't specify them, LabMAR will compute them numerically using a central difference approximation by default. So if I merely delete this, LabMAR will use numeric derivatives instead, and I can see if it works. And when I run it, I recover these exactly, so the problem is in the partial derivative. So I guess the point of this exercise was not so much look at the partial derivatives, but try and go through the process of validating the assumptions. Start with your model, try and figure out how to test your model. Don't duplicate your model code in different places. Make sure you encapsulate it well. Use standard best practices for programming, just like you would everywhere else. So this is an example of the layout for that 2D array that is the Jacobian output, the partial derivatives. In this particular case, I just wanted to show how it was laid out because this is not done well in our documentation and it probably should be fixed. If we start with a basic exponential function here, a e to the bx plus c, so a, b, and c are the parameters. The partial with x, partial with respect to b is this, and partial with respect to c is just 1. The way these are laid out in this part of the model function is each column represents a partial with respect to a particular coefficient evaluated over each of the x values that are input to LabMAR. And then the next column is the next partial, and the third column is the third partial derivative. So if you ever need to figure out how to lay it out, remember that the order A, B, and C is also the order that you are indexing out of the A array here. So A is the parameters. The first index should correspond to the first column. So that means that this, I'm assuming that this is A, this is B, and then the third index is C. Make sense? Okay. Next forum post. So constrained nonlinear curve fit can properly handle the function like this. So that's a direct quote from the original poster. The problem is that when he runs his VI, he gets this error -20068. Input parameters have at least one element that's one of these exceptional values. So let's take a look at that. If I run it, indeed I get the same error. If I click continue, I do seem to get something that comes up. So looking at this graph, the white squares are the data points, and the red is the fit, the best fit curve that comes out. And I get some values here, but I get this nan residue, and I have that error that I don't know where it came from. So looking at this code, right now it's again cleaned up considerably from the original post. Of course, most people don't post to the forums with beautifully written code that's ready for exposition, right? You're hacking away and something didn't go right, so you try about 10 different things and then you throw it all up on the forum. So anyway, this is distilled down to just a single call to LabMAR. And I wrote this little VI to just show some standard kind of graphs here. Here we're looking at the data is black, the red is the initial guess fit, so the parameters, the initial guess parameters, and then blue is the best fit. And then down here we're looking at the residual signal, which is the original data minus the best fit curve, or minus the initial guess curve, one of the two. Well, again, looking at an error that says in for nan problem can occur one of two ways. Either the coefficient update in LabMar gave some kind of error, caused a problem, or your model function, again, produced a nan or an int. Now it's propagated through and caused an error somewhere. So normally the linear algebra VIs in LabVIEW will produce, they may produce an error, but if they error, they will typically produce an empty output. So the fact that we're not seeing an empty output, like for example the best fit parameters still show up, indicates to me that it's probably not in the coefficient update, but it may be in the model function itself again. So if we look at the model function, the model function is pretty straightforward, and this is the original poster's code, so this is quite nicely done. Here we have kind of a complicated exponential function here. The one thing that jumps out is the natural log. And the domain for natural log, of course, is positive values. So if this value could ever become negative or 0, we have a problem. So this is indeed the problem.
Quick note from the remote audience. So Fab just mentioned that that perhaps the VI could a better error reporting. Maybe get some.
Yeah. Yeah, we could. So Fabiola said that? Yeah. I agree. The LabMar does not a bad job of at least outputting errors. It does use the error cluster. As I'm sure everyone's aware, the analysis functions for the most part do not output error clusters. They use the extremely comprehensive error codes, and they become kind of difficult to figure out. So I would very much like to see error clusters everywhere and more comprehensive error information. Yeah. So the fix in this particular case is merely to constrain the input of the natural log function using in-range and coerce to be between machine epsilon and positive infinity. So this assures a non-zero positive value.
I don't mean to backtrack if I am, but I don't know what X and Y are in the VI.
Sure.
But I guess what is this function? I can't really the title bar.
You mean the name of the VI?
Yeah, sorry.
Okay, no problem. So the question is, what is the name of this particular VI? And it says LN fitting model fixed. So this is what I think the original poster named it LN fitting model, LN being whatever his application was. And this is the model. So we would pass some reference to this into the
LN there is not a reference to natural log?
LN.
Could be. I honestly don't know.
But it could also be, Logitech natural or for whatever.
Yeah. It's hard to tell.
So the forum poster has
No, this is what I did to fix the problem.
Is there any step that you were altering in the way that this makes sense for the model?
Well, not necessarily. So the question is it possible that I was altering the inputs in a way that doesn't make sense for the model? And actually, to be honest with you, that is true. It's possible that LabMar will take a step, will try and try out a new set of coefficients that will be very close to 0 and maybe step into 0 or slightly negative. It just may do that. Maybe it takes too large a step. Maybe your model isn't describing the data terribly well, or there's enough noise that the least squares fit pushes it in that direction. So if there's sufficient noise, you could easily get that condition. And the only way to avoid it happening is to make sure that your model handles that case. So that's what you would do here. It's not a guaranteed fix to just constrain the inputs to all of your functions. You may, because I'm using a kind of a nonlinear thing in here, if you're hovering or stepping near 0, you may face some convergence issues, but at least you're not going to be dealing with errors like infant and. Right? So again, this is a kind of verify and make sure that your model is doing what you think it should be doing. Okay. The way that I actually found it was I basically backtracked the error. I found the error code coming from the model function, then back through the numerics with a probe, and I found where NAM was coming from and realized that the argument was negative.
Yep. Okay, so, few question about curves. So these model VIs, are they, so do I understand correctly that you have this curve fitting algorithm and then write a VI that contains curve to achieve this?
Yes.
And then pass a reference and, generate coefficients that will plug into this equation.
There's a VI template that you can use with, to start with, rather, that will give you the right connector pane. So basically a pretty basic starting point. There's not a lot in the template, just the connector pane and maybe one small comment on the inside. Yeah.
Right.
Sure. So now let's get to something a little bit more interesting. Here we've got a poster who wanted to do curve fit with prescribed end conditions, and it took a little bit of back and forth before it's clear what exactly end conditions meant. Basically, what he was looking for was a way to define a piecewise model. So in one portion, one set of values of X, he wanted some model. In another section, he wanted a different model, and he wanted them to be continuous, for example. So this is a pretty common. There's a number of posts that are like this. This is fairly easily done in LabVIEW using the interface that we have now. So what I did for this one, in this particular case, I replied, and this was I just made an example. So the example I chose was for every X value that's less than some parameter, so XC would be a parameter of my model, I want to have an exponential type model, AE to the BX plus C. Otherwise, I want everything above that to be aligned. And I wanted to have two conditions. I wanted continuity and smoothness. Continuity means that the two models meet at the same point. Smoothness means that the slope of each model at that point is the same also. All right? So the continuity restriction means that if I substitute for the y exponential and y linear, I get this expression here. If I take a look at the smoothness constraint, the derivative of y with respect to x has to be the same for both models. So this means that on the left, this is the derivative of the exponential, and on the right, the derivative is just m. So it means that m, in order to satisfy my constraint, m is already specified. I don't actually need to fit for it. And if I further take this m and substitute it back into the continuity constraint, I can now solve for y-intercept. So because we have two constraints, there are two parameters in the linear fit portion. Those two become now not free parameters. So you've lost 2 degrees of freedom in the model. So take a look at this. This is what the model looks like. Here we have the exponential portion of the model. And here's the x values coming in, and then here we're doing a threshold, so the last parameter is xc. We're finding what index that xc is, and then we're splitting the x values. So the x values on the left go to the exponential path, the ones on the right go to the line. We evaluate both models, concatenate the result, and output that as our model. Right? So this is the result of a fit. You can kind of see that the portion over here is linear, but I picked some really light noise, so it's not obvious what's going on. Rather than adding Gaussian noise, though, I chose to do something a little more drastic. And if we run this, my raw data is blue, and the best fit curve is here. So here's this would be very bad data, but you can see that here we've got the exponential portion, and right in here it transfers over and becomes linear. So we can do all kinds of fitting like this. Unfortunately, this is a somewhat manual process. We don't really have a way of doing any kind of symbolic work, so you could do this kind of substitution automatically in a very clean way. So there is a certain amount of work on your part in order to make something like this happen. But it is possible. So the next posting is another nonlinear model with a linear constraint. So in this case, I can't be clever and sort of incorporate the constraint directly into the model. So this is a little bit harder problem, but it is doable. This is a graphic that was part of the original posting here. So what the poster was asking for was to minimize this Q function. All he's doing is expressing the least squares function here. So the AIs are actually the Y values, and then this 10 to this power is our model function. But this is the kicker here is we have this constraint. Keep in mind that the X and C's are kind of reversed in this problem. This is just the nomenclature, the notation that was used. In this case, the parameters of the model are X, Y, and Z. And BI, CI, and DI are the domains of the function, or part of the domain of the function. And then AI is the range of the function. So there are two ways that you can address this problem. One, rather than using curve fitting per se, we also have a constrained nonlinear curve, or a constrained nonlinear optimization rather, function. In order to use the nonlinear optimization, you have to express this entire function, not just the model. So you have to do the entire least squares function. But the nice thing about it is you can express this kind of linear constraint very directly. So it makes the constraint handling very simple. The drawback of using the nonlinear optimization is generally going to be a performance hit. It's going to be slower than one. And the other way is to actually attempt to construct a penalty sort of function and use LevMar sort of to indirectly handle the constraint. So this is a classic technique in optimization. Take a constraint, penalize it, or create what's called a barrier function, add that to your original cost function, and make this larger cost function out of it. In this case, we're going to kind of look at the constraint as a second curve, and we'd like to make the distance to the constraint 0, and then we'd also like to make the distance to our data as close as possible. So in order to make the penalty term, we split the constraint into two halves, and I'm basically going to rearrange it so that I have the left half, so -1, and then I'm adding the center portion to the left side, so I have -1 plus this. And I'm taking the max of this one, this term, which is the right-hand side of the constraint, and 0. So basically, if the constraint is under 0, I don't care about it. It means I'm actually okay. The constraint is satisfied. So I don't want to penalize myself for being far over, well in the feasible region. So I'm going to take this max function, I'm going to multiply it by some constant, and I'm going to add that to my original Q. And that's the way I'm going to model it. Okay? So if we look at this code, this is the optimization using the constrained nonlinear optimization. This is also a VI reference-based. It's a different connector pane, but it works the same way. The objective function is evaluate my power of 10 model, subtract my y values from it, square it, and sum. So this is that key function that we saw in the beginning. And then coming out of this sub-VI, we also have the inequality constraint. So if we look inside this, this is simply the A, B, and C multiplied by the X, Y, Z added together, and that becomes my inequality constraint at every point. So it's not just one constraint, it's one constraint at every value in the domain. We have like n constraints that have to be satisfied. And then on the LevMar side, here's the LevMar code, here's the model function. Here again, we're evaluating the same power of 10 model. But here's the second portion of it. This is implementing that max function that I was showing on the slide. And so we just concatenate this. And if I run this, the top graph is showing the best fit curves along with the data. The bottom is showing the inequality constraints. So inequality constraints, black is the upper limit here, and the orange is the constrained nonlinear code. And if I turn off that, you can see that the LevMar and constrained nonlinear are on top of each other, so they're giving the same result. But what's interesting is that if I were to zoom in a little bit more, you would see that that constraint is not actually active. It's not doing anything. So I'm not showing any constraint violation. If I look at the parameters, they're both identifying the same parameters. This is the original code. I wanted to see what would happen if I forced one of the constraints to become active. So instead of 0.036, let's make the upper bound something like negative 0.05. If I do that, notice the LevMar reports a violation. And if I zoom in again here, red is the LevMar code. The constrained nonlinear is doing a pretty good job. It's in the feasible region, but LevMar is not. It says that LevMar is balancing the constraint violation with the distance to the original data. And all I've done is weighted that trade-off, but it's really hard to use that approach to make something that's absolutely in the feasible region. So you have to play some tricks. For example, increase the constraint K value. That would allow that to become smaller, but it's still not going to solve the basic problem. So these are just some ideas of how to handle this sort of thing, but this is a fairly difficult problem. This is another sort of fitting problem that comes up fairly commonly. I think I've seen at least 3 postings for diode equation. In an implicit type of equation, you can't really solve for y. You can't get y equals something, some function of x and a. So what do? I mean, how do you solve that problem? The answer is that you don't try and solve for y. In this particular case, we look at the thing that we're trying to solve for. Our model is going to be the entire x and y. Think of it as lifting the problem from a 1D, or a 2D problem rather, to a 3D problem. And now we're treating x and y as domain, and we're saying that we want all of our z values to be 0. So if I just subtract 1, I get this expression, and I want every z value, every range value to be 0. I could take square root of this first and then subtract 1. That would be a slightly different way to pose it. All of these are valid. Does that make sense? let's take a look. This is a shipping example. We take a look at this. This is the elliptical data. This is what the model function looks like. It's exactly what was on the slide, and then here's the square root, and then we're outputting for each of the domain values. Okay. This is pretty straightforward. So I wanted to cover at least one numerical issue. Switching gears from the LabMar fit, going to constrained or to the general least squares fit. General least squares fit fits functions of this form. If you have y equals a0 times f0 of x plus a1, et cetera, basically this is a linear combination of the f's. So the way this model is expressed is we have y equals h times a, where a is a vector and h is a matrix. The h matrix is of this form. Each column is a function. So the first column corresponds to f0 evaluated at all of the x values. The second column is f1, et cetera. So it's a linear problem, but you can solve some pretty interesting extended problems with it. In this particular case, the customer, the original poster here said, here's basically a polynomial fit, but it was a polynomial fit in 2D, so he was using x and y values in the polynomial. He said, if I use a 6-term polynomial, everything seems fine. If I use a 9-term polynomial, I get these outrageous values, and I don't know how to interpret the coefficients, so I was looking for some guidance. So in the 6-term case, this is what the function looked like. And in the 9-term case, it was just this polynomial here. So if we take a look at the data, there aren't very many data points. This can be a problem right away. Here we're just looking at the data and the best fit curves. And then down here we're looking at the residual signal. So given the scale here of on the order of thousands, the fact that the residual is on the order of 0.01, 0.02, that would seem to me to be reasonable. So if we change the length of the polynomial from the 6 to the 9 case and run it, still the residual is doesn't look too bad. It's a little worse, which is a little counterintuitive. If you add terms to a model, why does the residual go up instead of down? So that's the first indication that there's something strange going on. With problems like this, the only time that you have a problem with general LS fit is if the input matrix H here has a really bad condition number. So recall the condition number is just the ratio of the largest to smallest singular values in the matrix. A large condition number means that if you invert the matrix, you lose a lot of precision. It means that there's lots of really large values and really small values, and you're going to have numerical issues. So there is a VI in LabVIEW to use the condition number. And when we take a look at the condition number of the original problem, it's enormous. It's e to the 23rd. If we go back to the 6-term case, it's e to the 16, which is still really large, but is apparently giving results which, for the original poster, were making sense. When we take a look at the coefficients, notice the first 3 seem to be quite a bit larger than the last 3. We go to the 9 case. The first one is now really small again. The next 2 are okay, and then we've got a bunch of really small values. So I can't look at the numbers and make any real sense out of that.
question with regards to, the fitness of LabVIEW that you're using during splitting operation. So I'm in a situation where I'm doing matrix conversion with something that's actually not that far off from this. And, yeah, should I just expect the difference between LabVIEW 64 and 32-bit in terms of whatever DLL is running behind the scenes?
Yeah, so the question is, should there be a difference between the matrix inverse given a 64-bit or 32-bit version of LabVIEW, right? Well, the answer is maybe. So underneath the hood, all of the linear algebra in LabVIEW is implemented using calls to the Intel math kernel libraries on Windows and Linux. And I can't remember if we're still using the Apple libraries on the Macintosh. But given that you have 32 or 64-bit installer, we may or may not be installing a 64-bit version of MKL, which would possibly have different results. It could be different. The thing about this kind of numerical behavior, the order in which you multiply and add things begins to matter, because depending on how you cancel out the values, you may lose precision in a slightly different way. So even something, and I'll show in a minute, there's a number of posts that compare LabVIEW's results to Excel's linear estimation function. And why is it different? Or why is it different than Origin Lab? Or why is it different than anything? If the problem is well conditioned, everyone's going to agree. We all are going to get the same answer. It's always when you run into a numerical issue that you begin to see problems. And again, depending on how the algorithm is implemented, it could be the exact same algorithm written out on paper, but depending on how it was coded even, it could make a difference in the numbers that come out for these exceptional cases.
I'm not using linear algebra functions, but I do have pretty complex numerical algorithms that for numerical results, like the 9th decimal form. Yes, so it's only coming out of the US. But I'm curious, is there tutorial information by NI on how to solve an algorithm?
Yeah, so this is forward and backward error analysis of algorithms. Look for textbooks on how to actually set it up and analyze. That's really all I could say.
Probably obvious showing.
Any other questions?
Fabiola wrote online, so then is it a different implementation, Mac, Linux?
Yes, at least not the curve fitting algorithm itself, but the underlying linear algebra that the curve fitting relies on. Yes, it is a slightly different. The functions should return the same results, but depending on how those functions are implemented, you could get slightly different values in these very difficult cases. So yes. So to make a long story short with this function, the solution here is, instead of doing the linear fit or the general linear fit directly, the idea is to take the H matrix, basically take the model and scale it, scale all of the columns so that they don't have such large and small values. So the way we do that, here I'm taking the H matrix in, I'm taking a column at a time, I'm finding the mean and standard deviation of the column. I'm basically doing a linear transformation of each column, so I'm subtracting the mean, dividing by the standard deviation, and then doing the general linear fit, and then at the end, this is taking the coefficients and undoing the scaling that I just did beforehand. So I can pass that through the model. And again, it requires doing a little bit of algebra, but you can get the results on the back end and then restore your coefficient. The nice thing about this approach is, take a look at the scaling approach. Instead of having a condition number of e to the 23, we have a condition number of e to the 6. So it's a huge, huge improvement. If you can do anything on the front end to avoid the numerical issues to begin with, you'll be much better off than trying to fix a numerical problem after the fact. So doing this kind of scaling is really the way to go, but it does require a little bit of effort. Okay. So here's a couple of additional posts. These are the Excel linear estimation posts with various people replying. I have one more thing I wanted to show, and then I'll be done. Nonlinear curve fit performance. How can you make curve fitting go faster? The number one thing that you can do is to make your initial guess better. It sounds really simple when you say that, but the closer you are to your final answer, the less iterations the algorithm has to go through it, and it is an iterative thing. So the fewer iterations you have to make, the faster you'll get there, the faster the algorithm will run. So that doesn't mean you just put the right number there. It means you develop a simpler algorithm to do an estimation for you and get you close, and then engage LabVIEW on the better starting point.
When people have performance issues with curve fitting, is it because they're like trying to do one curve fit and it's taking a really long time, or because they're trying to do curve fitting in a tight loop?
Yeah. Both. So I've seen people that are doing curve fitting where the model function was a 10th or 15th order ODE simulation, variable step size solver in the model function. So every step you take is an entirely new simulation of a system of differential equations. So that's a really heavy model function. It's very expensive. On the other hand, the example that I'm going to show is a simple exponential fit, but it was the application was in LabVIEW RT. So this was a tight inner loop kind of thing where they needed to run absolutely as fast as possible with low jitter, if we could arrange that.
What type of application on RT?
Honestly, I didn't get that information. So
You could, a motor control would be an interesting example, something like that.
Why does that need curve fitting?
Well, you're trying to sense where something is, and you kind of want to connect a couple different points. You want this to go from here to here, and so you want it to kind of maybe a nice trajectory between 2 points.
Sometimes you have for example, a motor model, but the model changes over time, temperature. There's a tempco in the model, and you want to recalibrate on the fly. A recalibration is generally some kind of model fitting. So the second best thing to do is take a look at your termination tolerance. There is a termination criteria. If you need it to run faster, make sure you need all the bits that you're asking for, all of the accuracy that you're asking for. The third thing, we've already seen the partial derivatives. Use the partial derivatives. If you want to go fast, there's two reasons for it. Number one, you don't have to use the numeric approximation. And the second is that when you get close to the answer, the partial derivatives are more accurate than the difference equations. So you will, when you get close to a difficult problem with numeric derivatives, the thing chatters around the answer before it converges sometimes. But if you have an actual correct implementation of the partial derivatives, you don't see that behavior. So when you get close to the end, it has better behavior as well. It is possible to go in and change the numeric derivative selector. So I said it used central difference by default. You can change that to use first order forward difference to try and reduce the number of calls. There's one other parameter in the algorithm. There is a lambda parameter. So LabVIEW, when it takes a step, is basically a trade-off between what's called the steepest descent step and a Gauss-Newton step. Steepest descent uses gradient information only. Gauss-Newton uses gradient and curvature. So LabVIEW will attempt to take a step, check to see if it reduced the cost function, and if it did, it will change the lambda value to begin to prefer the Gauss-Newton step. So it wants to take bigger steps. But if Gauss-Newton, if curvature is not a good fit for the model, so for example, you take a step and the model function didn't decrease, it got worse, that means we need to rely on the steepest descent and become a little bit more robust. So it trades off between taking large steps and robust steps. So lambda has a starting value. The starting value prefers the steepest descent right now. I'll show you where that is. Here. This value here is lambda, and its default value is 10. This setting is here because we use a set of NIST test functions to validate the correctness of the LabVIEW implementation. In order to pass the most stringent starting points for all of the nonlinear models from the NIST test suite, we have to use a starting point of 10. If you know that your model is doesn't require this, you can change it to something like 0.01 or 0.001 and try and take a step that's more Gauss-Newton-like. And it can often shave a good number of iterations off. So I don't know that I have time to go through all of the different takes here. Let me just open up the model function and show you some of the things that I was playing with here. In order to try and make the model function run a little bit faster, here's the way you would typically implement this model function. It's just an exponential function, and here's the partial derivatives. I get my matrix out. The problem is that I'm constructing a matrix using build array every time, so there can be implications on RT by doing this. Rather than doing that, if I do some kind of pre-allocation and replace columns, so I'm pre-allocating the array on the first call and then just replacing columns here, this ends up being quite a bit faster. On the algorithm side, it is possible to add an initial guess function here. So this is my attempt to get a better initial guess. If we run this as is, put this back to 10. Right now, this is standard LabVIEW using the using the fast implementation of my model function. So the model function is orthogonal here. If I run this, the time it takes is 928 milliseconds, but notice the curve fit results are terrible. So the blue is data and the red is my curve, and that's a lousy fit. That's no good. One way to try and improve the robustness of a fit is to use some constraints. As LabVIEW attempts to converge, it may wander in an area that's very far away from your final result. You may have a range of values for each of your coefficients that you may be able to specify. So in this case, I have two separate ranges. If I use the typical here, notice the fit is much better, and I actually have dropped a little bit of time. So I'm now down to 497. If I choose to start using an initial guess to try and improve LabVIEW without using the constraints, time is worse, but at least I'm getting the right fit again. If I use the initial guess on the bounded, it gets better. But what if I change that lambda value? Instead of being 10, let's make it that 0.01 I was doing before. If we run it now, it just went to, I just decreased my time by 2/3. So that was a significant change for this particular problem. It's very problem specific. And so the final thing that I did was here, the last point in the slide is roll your own. So if you absolutely need to go as fast as possible, start getting rid of the call by ref, start pre-allocating fixed size arrays, start sort of including the model and the algorithm together and see where you can make savings, combine loops and that sort of thing. So when I did that, so I enabled a pure Gauss-Newton. I got rid of a lot of the stuff that was in the LevMar, and now I'm down to 115 milliseconds. So almost an order of magnitude improvement in performance from stock and naive implementation of the model. That's all I had.
Right. So, you want to roll right into the next presentation, or take a couple minutes?
I need a second anyway.
You need a second? All right, let's take 5, 10 minutes. We'll start 4 minutes. 4 minutes. Enough time to run down the hall.
So, I'm so used to using the quadratic fit functions, polynomial fit. The output of the functions, I know, well, I guess there's 2 things. It's just, if you already have a model, what's the purpose of the fit again? You already have a model, right? You have a model, you have a VI that you put values into, and you're getting values out of it. Right? So if you want a value, you run some values on the thing, right?
But the model is parameterized. So if you have a model or a loader, for example, you may have a so you build a model with these coefficient or these parameters. Well, sometimes you got to find those parameters. So if you specify an R value of 100, you can measure it in the value. But sometimes you don't know what that is. There's so then sometimes it's better to actually simulate the model, get some input output data, simulate that, and model. Now you've got to try and convert it. What are the coefficients of that model? Once you've got that, then you can use the model all the time. Getting those values.
Right, but I guess that was the thing that everything that you were showing, in order to do the fitting, there's a model into the fitting algorithm.
But it's a model that has parameters change. You're passing in these values as mark as you go, and tries to make it get close to the Y data. That's what it does.
So you have a different model that you do know things about, and then you go ahead and
Well, even if you don't have a different model.
I was looking at
You have a model that's
only got a use case. Because if they're going to fit,
LevMar, R and C, R and C.
you can drop that until we will drop it out. Like, that's the problem. You can't fit them on a single index input.
Yes. Well, LevMar is tweaking the values of to the actual algorithm itself, into the model. Okay. That's very different than the big model.
Yeah, in the case of like quadratic, it's
yeah, exactly. Okay, perfect.
I'm all in favor of that. My wife, however, is she one of these, humanitarian.
Somebody want to spit me out that join me code? Give me a second, let me wait for it to start presenting here.
A lot of money for that.
imagine I would be. Hit me.
647-603-543. But I don't think my job is to ask questions.
Wait.
All right. I don't know what I'm doing. Yeah. I used to know how to do this. Yeah, wait, Norm, I thought everything was shut down.
You saw that, huh?
I did, yeah.
So this is something that I saw earlier today, and it made me very angry. So.
Straightforward.
Let's close the program.
Everything.
But everything's already stopped working.
It stopped working correctly. See, that's the important adjective there. It's still working.
Incorrect. Like,
Yes, exactly. Including.
It's on Facebook, snag it. That just made your day, didn't it?
Put yourself in air dialogue.
Forget it, just go home. There's no chance of anything working. Let's see, what am I talking about today?
You're done. End of story. Just put that in air dialogue. Do over.
Uh-oh. Oh.
actually have air.
Alright, I probably should open up this as well. And guys and gals. Fabiola, how you doing? You on the phone? Guess not. Alright, so just to get started, I'm going to try to blast through this presentation real quick, just because not everybody's heard about this, so I want to try to get started.
Everybody, this is Norm.
Hi, everybody. I think I know pretty much.
Norm Kirchner.
First, there you go. So this presentation is in its entirety on lava. So I'm going to blast through it. If you want to check it out more, go on lava and look up TLB Prime. We'll get into that in general. Who here has not seen or heard me talk about TLB Prime? Anybody? TLB Prime, yes. Okay, that's a healthy enough version for me to actually go through this presentation. So I might just go through this as fast as I can. So in general, once upon a time a friend asked me, how do you identify a bird? And I thought that was interesting. I looked out at Katrina, said, there's a bird. But she was talking more about how do you identify the type of bird that it is. And just like, well, you pick out its attributes and you say, it's got a this, it's got a that, and can it fly, can it not, and eventually you can figure it out. In this case, even though you don't know the color or if it's alive or dead or just whatever, we can all tell what kind of bird that is. That's kiwi. So in general, we can all look at this and probably identify what it is without necessarily knowing what it does or if it's alive or anything else. It's a state machine. Most people can look at this and say, what is this? Well, we can also, we can look at this. Well, it's got some queues, an event handling loop, message loop. But the one thing that we do know is it is not a state machine. Hence, that's the as some people hide in the back of the room. It's not a state machine. It's been called if I'd use it, it's like the heavily quoted LabVIEW State Machine, but really that's it's a misnomer. All things wrong, all things together. So some people might be saying, how dare you say that my thing is in the state machine and that I shouldn't be coding with it, and that's my general statement, I suppose. My thesis is that not only is it not the state machine, there should be another one. Don't use this paradigm to program up your programs, and I'm going to get into that. So some people very much might say, why, how dare you, there's nothing wrong with my bridge. I've coded LabVIEW using queued message handlers for 20-odd years, and they've been working perfectly. Well, the reason potentially being is because he knows how to walk across this bridge. He's like doing one of these numbers.
And I've been writing queued message handlers for 20 years because we haven't had queues that long.
Oh, duly noted. But the reality is that what happens when the happy-go-lucky programmer starts after him, or the next guy on the team starts to use it, you end up with that bridge over on that side because some dumb schmuck decided to step on the wrong peg, or in turn started doing a happy dance on a button before you had a chance to disable it, or decided to in-queue another action after you in-queued 5 actions and were planning on in-queuing a different action, and you've in-queued another one in there, and you end up in this terrible rat's nest of flow control in your program. Well, let me see if these links still work. God darn it.
That would be no.
The rebirth of Norm's presentation.
Yeah. Give me a second, I got it here. There we go. This is the one. So this is
Those of you who are new, it is perfectly fine to mock Norman midway through. We learn more when he's stressed.
It's okay.
He rides on this stuff.
No.
And he will start jumping on tables, don't worry.
Yeah, that guy right there is usually the reason behind it. So why am I loading the icon? Oh, gosh. All right. So in particular, so this is going to be a fun thing. So I need to write a program. It needs to go 1, 2, 3, 4, 5 on the front panel there. So 1, 2, 3, 4, 5. Great. My program works. Well, so all of a sudden, your program user, mocked directly at me, not in the background. Like, it's terribly distracting. So, and I'll stop and then I'll just waste time. So.
We were laughing at the post on the screen that said, make sure we take a picture when you jump up on the table.
Oh, okay. Fantastic. So, so then somebody decides to hit start before, now I got a bug in my program. It's not running through. Well, what happened? Well, we'll see real quick. On the block diagram, I in-queue state 1. I in-queue state 1, and next thing you know, I in-queue state 2, and it keeps walking through, but if I hit a button, state 2. So we kind of see what's going on here. I'm using the action down here, or the state down here, to in-queue the next thing. But if I hit the button too fast, it's going to in-queue it before that comes in, and there's no flow control. So what does the savvy LabVIEW programmer do? Well, the savvy LabVIEW programmer goes, well, you know what? I'm going to fix the bug in my program. I'm going to go through, and I'm going to, when I in-queue state 1, well, screw that. I know I'm going to be doing state 1 and then state 2, 3, 4, and 5, so I'm just going to in-queue all of them in state 1, so it's more of a macro style, right? Well, that's fine to a certain degree. What is going on? Anyways, so I'll run the program. Let me go ahead and turn up my, actually. Exactly.
Norm just bounced.
Prancing across the room.
Norm doing weird things.
That's par for the course. Okay. So, of course, in this problem, I hit start, and it's great. I go hit start again. It doesn't screw it up. It goes back to state 1, but now I do a happy dance on start. And it stays in state 1 for 5 seconds. 1, 2, 3, 4, 5. 2, 3, 4, 5. It's obviously that I've got a program problem. Okay, well, let's go ahead and be the savvy LabVIEW programmer and code around it again.
Use high priority then.
We're going to get there in just a second. Don't cut me off. All right, well, so let's just get them all in at once. 1, 2, 3, 4, 5. That's fantastic. Now nothing can stop my program. I'm impermeable. I can do a happy dance on this.
But nothing can stop your program.
Exactly. So now I'm stuck, right? Okay, so we all saw that one coming. So the savvy LabVIEW programmer goes, well, how am I going to do that? Well, I know what I'll do. I'll listen to Stopper and say, ha-ha, I'm going to in-queue at the opposite end, right? So I'm going to do that. Oh, yes. So one.
Forms an existing API.
So I'm happy dancing and I hit stop. Oh, great. It stopped. Fantastic. My program is absolutely perfect at this point in time. Now, the problem with this one, though, is I still want it to do 1, 2, 3, 4, 5 and then stop. So how do I actually do that? How do I let it finish that 1, 2, 3, 4, 5 and then stop? Okay, well, hold on. Well, that's actually not even part of this, to tell you the truth. That isn't even coded in. But say now I actually at least want to do something before I exit. I want to do some like autosave or cleanup even before. So now here's an interesting one. So I'm going to do this priority queue aspect to it. I'm going to go ahead and say that I'm going to in-queue at the opposite end. My question to you is, which order do I in-queue these in? This then this or this then this? So I should reverse this. Okay. So you say do exit then save, right? So this is the one that I want to do. Now remember, when I hit exit, I want to save first.
Depends on if you're sure the key's empty.
I didn't save. So I should probably, right? So if I go 1, 2, 3, 4, 5, right? Saves, great. But if I just stop it, it doesn't save anymore. It doesn't actually exit. Crap. So what am I going to do? All right, well, let's go ahead and flip it around the other direction, right? But you should probably all seen, oh, whatever. It doesn't work. Neither of them work.
Does everyone understand why it doesn't work when there's nothing in the queue? Right.
Yes. So if there's nothing in the queue, it pops off the first one, which is exit, and then it pops in save, but by then it's already done with the whole damn program. The overarching issue with this is there's functional Play-Doh going on. So this is what the people in the Play-Doh Corporation would have you believe children will make with Play-Doh, where all the pieces are nice and separate and neat. And if you want to make that creature, after making that into that, you just go pop it off. That was me making noises and waving my hands, gesticulating, and for the people on the phone, and then, you make that creature. But what's the reality is that this is what you get when children play with Play-Doh, and adults, me included. But yes, the child in the background is very happy with everything, but you can't pull the orange from the yellow, which I don't know if you can really see down there, to make the new thing. That's what's happening in our program. We have an evil twin buried inside of our programs. If we are just using the standard queue-driven message handler, we have flow control coupled with actual actions in the program. We have a state machine. If we make our program and it's bulletproof and we're walking across our bridge and we tell our customer, don't press that button twice and don't share this queue and don't do these things, you've now made sure that they can walk across the bridge. But you have cooked the state machine into your program. And in order for somebody to understand how your program is about to flow, they have to go through each and every single action inside of the program to devolve what the program is actually, how the program is supposed to flow. And if you have any conditional logic, how many people have done this? When you are about to talk to an instrument or about to close a reference to an instrument, you say, is this reference even valid? Or, let's see, that's one that I run into sometimes. But there's certain situations, but the reality is we need to exercise that evil twin. We need to separate the flow logic of the program from the actions of the program, the things that it's doing, making this now your action engine, and this is now your state machine. So how do we go about doing that? Well, for most people, it takes a little bit of melting and reshaping of the brain. We've been so steeped in this idea of a queue-driven message handler for such a long time as like, this is the best thing since sliced bread to actually make the program. Even Actor Framework follows this similar paradigm where it gets a message and it just kind of does something right away. And you still have to deal with the fact that there needs to be some flow control, some statefulness to your overall program. So I guess the idea is, let me even bounce back a second. How many of us in our programs have different modes of the program, where in one mode of the program that's done with the queue-driven message handler, we have certain things enabled in grayed out, or enabled and other things disabled in grayed out to indicate what's going on. Those are different modes. Those are different states of your program. Your program is doing something very specifically different when it's set up like that. That's the reason that you gray things out, so the user doesn't interact with them. But you better hope that you gray them out fast enough so they don't do a happy dance on them. So, step one behind all of this is we kind of have to melt our brain a little bit and say that there needs to be some kind of flow control that should be handled by a state machine. But if you can think about it, what are the modes of the program that I'm working in? So if I'm doing a program, I do a lot of test and measurement applications where I'm doing, okay, I run the program. How many people write programs that you better make sure that you actually have the parameters set right before you run the program? Because if you don't have the right piece of hardware identified before you hit the run arrow, it throws an error. I've seen it too often. It's a poor user experience. And it's not, you wouldn't have to expect to type in your document first before you run Word and format it, right? So we shouldn't expect that of the programs that we make for our customers. So when I start my program up, it goes from, idle, and then I have a connected button, and then it tries to connect to my hardware, and then I have maybe another button that starts it sweeping, or starts it logging, or starts it measuring, or starts it doing whatever. Each one of those are different modes, and the programs respond to triggers in the system in different ways based on the mode that it's in. If I say close application, I don't want to go through the same set of actions if I haven't connected, or if I'm in the middle of sweeping. I might want to stop sweeping first before I start to shut down things and close out resources and then eventually close the program. I don't always want to respond to the same stimulus the exact same way every time. And so the way that I'm kind of envisioning this is a simplified way of the state machine. If somebody here is a purist of like what the true definition of mealy state machines, Moore state machines, the UML definition of entry actions and exit actions. There's a whole lot of stuff about state machine you can do. This is what I'm kind of proposing is a simplistic view where you say my state is defined as a mode of my program. It's really not doing anything except it's the brain of this mode of the program. And then everything that I want to do happens along transitions between states or back into myself.
Fabiola has a comment.
Yes.
I can read it. But the bad user experience is not because you're using a QMH, it's because there's no planning, design, and architecture beforehand.
Incorrect.
Developers are going to use the quote code and fix approach.
That's psychic.
Psychic or psychological?
Same thing.
Okay, so, but if you can all go with me for a second, let's see. I actually probably should show a. Let me see what I was trying to open here. What hyperlink was I doing? Great, didn't even say. So if you can go with me on this one, we're going to talk. Let's see, no. So this is my TLB top-level baseline template. For those of you who love it or hate it, the colors are mostly not there after you have all the structures in there, but it indicates here's my event handler loop, here's my primary execution loop. This is just startup and teardown code of the entire program. So something that's very, very familiar to all of us, not necessarily TLB, but just the basic idea. Screw the stuff on both sides. We've got an event and we've got a queue-driven message handler that's happening here. All that I'm proposing is to say the smallest deviation from what we know to try to do a little bit smarter program, where we say we're going to do that exact same thing. We still have the same list of actions, but we're taking all flow control out of this portion and making a very unique home for it and a very explicit state machine for what we're working with. Let me show you some examples. Questions?
Keep going.
Okay. All right. Go ahead. Yep. So this is a very simple program that allows you to select some things inside of a project and then very simply flip through their block diagrams and actually interface to them. It's a live block diagram interface. So a particularly handy tool. It actually packages up with TLB Prime in general. But here, can everybody see this zoomed in on the lines, on the interwebs, on the tubes?
It doesn't really render as.
That's unfortunate. Oh well. Then I will do it like this. That probably.
No, it is.
Yep. I'll just have to go in and out between each one. But this is the state machine for the very basic program that I've got. 2 states. There's not a lot going on. I'll open up another one that actually does stuff with tests and measurements in a minute. But I start up the program. It does some actions on the way to idle. You know, it does it sets up references. It saves values. It initializes shift register, whatever. And then it just sits there. And I don't know what it does along here, but it might do a couple actions. Maybe it just updates the display for a clock or something like that. But it just sits here in the idle state. And then it waits for a trigger. It waits for a button push. Triggers are things that happen in your system. Triggers can happen from external to your program, which is typically not something that you can handle in your traditional queued message handler. You don't want somebody else outside of your program sending actions or states into your program through your queue. You usually want to protect that through some means. I'm saying it's the same way with this, so we've got a button push. So in this case, I hit the load selection button. It does some actions on the way to being in the viewing state. So let's go ahead and follow that transition along for a second. So down here, I'll actually, people that are watching online can probably see it anyways. So this is my list. I finally now have a true state machine built into my queued message handler, where these are my system states: startup, idle, viewing, and shutdown. So if I am in the idle, try to be patient with this, it's a little bit jerky here. So I'm in the idle state, and if somebody hits load selection, I in-queue these actions, and then I move over into the viewing state. So the logic behind this program is the list of actions and then where you end up at the end of the day. This is already pre-coded. I'll show you the template in a little bit. This is already built. You kind of get a lot of this for free. You just have to put in what specific actions I want to do. So in this case, what's the active project? Collect and filter references, update the tree, load the items, update the display, and now I'm done.
You don't have a separate file of what? Nope, you lost me. Totally.
Damn it. What did I miss? So in particular, the way that this...
These queuing actions are back over being handled on your left-hand side?
Yes.
Picture?
Yes. There's two queues set up in here now. Typically, queue-driven message handler has one queue, right? That is we're in queuing states. No, we're in queuing actions into the system. And then we have a second queue, which I have now over here, which is our trigger queue. As we push buttons, as thresholds are breached, as things happen in the program, triggers are fired. And now the state machine is the one that is now digesting those triggers safely, figuring out what to do with those triggers. And now if you actually look, I don't know, actually I'll zoom into it over here, very purposefully so. Come on. Stop my synergy. Just kind of a funny thing to say. You'll notice this is not going into there. This is my typical queue. Typically this queue reference would go into your action handler, and you would be in-queuing other actions from given actions, possibly breaking up any sense of flow control in your program overall. I'm saying don't do that. Only let the brain of the program be the thing that can dictate what actions actually happen.
So when you start modeling, I'll try
Right.
too formal with it, but I'm trying to relate what I know to what I see.
Yeah.
And you use AMC to make this thing happen first. Seems like you've only got exit actions from the data.
Exit or
You don't
entrance?
define entry actions, because split it if you're transitioning from one state to another.
They're merged together in this case, really. Because I'm saying that everything happens along the transition.
Exit/entry action.
Yeah.
You only define one action.
Yeah.
And you don't allow a new action where you would stay in a state differently.
That's kind of
You require transition back to the state.
no. If that would almost implicitly be the idle. If you get no trigger, what do you do in a no trigger
That
scenario?
is the transition on idle.
Yeah. Transition on idle.
He doesn't have basically a sub-state machine within the state.
Yes. It kind of stays in the state, but it exits and comes right back out. So in this case, I'll show you if I am in the. Here you go.
There is a technical
Right here.
difference
If
between
I'm in
idle, leave and come back, and staying within a state.
Okay. Oh, yes. Yes. That is where I deviate from the bigger picture of the formal definition, if you really know. But I'm just trying to get people that do queued message handlers just to even accept the idea that there's flow control that needs to have a different home. Sorry. So in this case, if I'm in the idle state.
Go ahead, keep going.
I'm bad with people talking to me. So, you can ask the question. I'm okay with it. Oh.
What was it? I said that's the same mentality that got NI to start teaching messaging.
Not wanting to dwell on the
Simplifying the truth so that they would accept it.
That it's complicated? It's gotten a lot of people pretty darn far over the years, though.
Yeah.
That must have $1 million. So yes, in this case, idle and none.
Pass on your money. My Q1
All right, so, moving forward, different discussion. Tangent, warning, tangent.
Where are you in-queuing the new state transition? You got that secondary queue.
In-queuing the new state transitions?
You're dequeuing from a different queue in order to drive that in there.
Queue over here, yes, I am dequeuing from the triggers, the trigger queue, effectively.
Okay.
And I in-queue more actions, and then I dequeue my actions over to the left.
Right, where are you in-queuing into the trigger?
Oh, anywhere, period. Everybody can, the trigger queue is for everyone.
Including outside of your...
Absolutely, because my program has been designed to be able to handle triggers safely. That's the whole thing. I now have a flow control where triggers can come from anyone. And the brain of the program is now completely relegated to handling triggers based on the state that I'm in. If I'm idle and somebody says, poop on the floor, tough luck, I'm idle, I'm going to ignore it.
Wait, okay, I missed something. So not everyone can in-queue action.
Correct. The only person, ideally, if I could, I'd wrap that up and I would only let those actions be in-queued right here.
Okay,
So,
I'm
yes.
sorry I had your left and right. So essentially, all you've done is you've created priority queue by staging the two queues. You have the one queue that the world can talk to that you handle, and you have a secondary queue over here that is basically gets a higher priority for your internal work.
But they're two different in-queues. A priority queue means that the same DQ can get both.
Yes, I agree with it. I acknowledge the subtle distinction, but it is, this gets priority to be handled over whatever else comes in, because you're not going to be, everything, so this one cascades into the first one only after it's been processed.
Sure. But it doesn't need, okay, yep. Continuing. There's a whole lot that could be talked about. So, not that I want to glance over it completely. Let's see. But if I'm idle and I hit the load selection, it does those things, and then it transitions to that. So I would say that these are the things happening along the transition. That's where it ends up. Now I can watch the flow of my program if I'm in the viewing state. Okay? And now nothing happens. Now I can see what happens when I'm viewing and nothing happens. As opposed to having to scan through every action and say, oh, wait a minute, what parameters is every action looking at, and is this action safe to be called in this, it's unprotected. Every action is unprotected unless you have somebody directly controlling the flow of the program. Yes.
But you got the same problem here. You still have, go back to on the right case structure wherever you're doing a whole crap load of stuff all at the same time.
Oh, that's not a crap load. I'll show you a crap load.
Anyhow,
which is different than
somebody from the outside world can still jump into that queue at any given point in time.
And that's perfectly okay. As long as if I am in a state, if I am in a state and I get a trigger, I'm okay to handle that trigger. I still have to program this guy up, but I can get a trigger in any order. And I can choose to drop the trigger on the floor, I can choose to handle the trigger, but you did not have the chance to handle an action if you were directly in queuing things over here. You had to handle them. You had no choice but to handle things that happened. And then you had to cook, how do I handle this thing inside of my actions itself?
I wish you had coded up the step 1, 2, 3, 4, 5 in.
Well, I'm glad you asked.
Okay.
So this is a much simpler version of it, but it still very specifically has two separate queues in this case. There's my kind of action queue, which erroneously I'm still wiring through, whatever, right? And then I'm in-queuing my actions up top. And so if this is my state model, I've declared the processing one is the state that I go to after I'm doing 1, 2, 3, 4, 5, or while I'm doing 1, 2, 3, 4, 5, and then goes from there. And so if I am currently processing and nothing happens, let's see, make sure I get this right. It's been a while since I've done this one. So this is a scenario where I'm actually, let's see, there's a couple different ways to skin this cat. But in any case, there's no actions that I'm really doing on the way to starting to go to processing. So what I do is, if I'm idle, and I get, well, that's the thing, now I actually have a home for all the flow control. That's another big part of this too. So now I can just figure out what the flow of my program is for over here. So if I'm idle and somebody says start sequence, I'm not going to do anything with it, but I'm going to go to the processing state and tell processing state start sequence. Okay? So now I'll go to the processing state, and then start sequence, and I'm going to do 1, 2, 3, 4, 5, and then I'm going to go back to the processing state, to which if nothing happens once I get back to the processing state, I'm just going to go back to idle. So 1, 2, 3, 4, 5, and then go back to idle.
So what happens if you start twice in this scenario?
If I hit start twice, I'll go ahead, it's going to enqueue to start sequences along the way. So the one thing I would like to mention along with all of this, this doesn't prevent potential scenarios where you'll end up possibly in this infinite loop of doing things. If you have one thing enqueue a trigger, which enqueues another trigger, which enqueues another trigger, it's going to follow your instructions. So you're not saving yourself from that behavior. But you'll be doing it safely, because the actions will complete before it enters into the state, and it will do everything that it needs to before it says, what do I need to do next? So you're never really jumping in front of anything that you shouldn't be doing.
That's what I'm missing. You're only executing one action, and then you're reevaluating whether you've got another trigger, right?
I'm executing all the actions. You're missing this. Sorry. There's a critical piece of information. I'll go back to the larger one, because it illustrates it better with the colors.
You only do the trigger on no action.
Yes. So I only look at the brain of the program once all actions are complete. So I completely extinguish my action queue. So my transition, so at any given point in time, my action queue only has the current transition inside of it, which is extremely powerful.
So it really is a priority queue, because you evaluate one queue, you train it completely, and then you evaluate the next.
Yeah, I guess I'm making the actions the higher priority.
Yeah.
Sure. Okay.
Okay, good.
Yep. Okay. Yep. In that logic sense, I guess you could. Yep. So yes, but that ends up being the difference here. So there are questions that people ask along the way of like, hey, what about if I have to stop now kind of scenario? And I say in most applications that you're dealing with test and measurement, do you absolutely have to stop on a dime? No. Most test and measurement applications, I don't have to stop on a dime. The minute I hit the stop button, I don't have to stop instantaneously. Now, that's not saying that everything isn't, but even in that scenario, much like the car wash example, right? There's some allowed latency between X and a Y, right? So that gets into a bigger, deeper discussion of how to handle more corner cases with them. But I can tell you right now, we've been building a lot of applications with this, and the reality is we don't have to stop instantaneously. We're doing test and measurement, starting to do things, even in an application like this. So, see if I can get back to the program. So, a couple different benefits of going this route. Ease of documentation. It is a defined home for where the flow control exists. It also is easier to declare how the program is going to run based off the state machine type of diagram. With your typical program, the way that people used to describe how their program flowed, I did this for Core 3. The guy who created the course, he has a page that goes from the ceiling to the floor with a flow chart of how the program operates, because that's the only way. If this happens at this time, then go here and that. It's very difficult to describe a program in terms of a state machine unless there's a state model in it somewhere that you're describing. Functional containment, now there's a defined home for that flow control that you can go to. What's wrong with my program? Is it getting bad errors, or am I going to try to shut down a piece of hardware at the wrong point in time? Reuse of actions, this is one that's kind of interesting because the challenge ends up being you can make I could put all of my code that I want to do if I were to just look at this portion right here and put all the code for these actions buried in this structure. It would be no different. My programs would run exactly the same. If I put all the code that was get active project, collect and filter references, I could put this right here and forget this entire queued structure over here. And now I would have more of the traditional LabVIEW State Machine. The challenge ends up being is I no longer can reuse these specific actions. Or I have to put each one of those actions into a sub-VI, which has its pros and cons as well.
What about the concept of a queue that has an array of states?
For the traditional queue message handler, there was one queue. You queue an entire array at a time. So one element of the queue is array. All these different. That's all I've used.
So it's got an atomic action now that's doing separate things. Right. And that basically turns into splitting those into two while loops. What I at first expected was with complete exhaust functions we can go over. It's effectively what he's got by bridging it with that Boolean up there.
Yeah, David's describing a different way to do what you've done.
Yeah.
Okay.
That's why I didn't use it.
So I will talk about why I put this into one loop for the moment, because I not quite see well, if you in-queue it all at once, where are you going to put all things that you want? Because you only want to in-queue all things that you want for the trigger based on knowledge of what state that you're in and other things about the program. But there's a few different things. I wanted this inside of this loop because of this data. This is a very large, potentially magnanimous chunk of data that your state machine might use its information in order to determine, wire it down in there, what do I do in my program? If I'm doing a looping, if I'm going to do a sweep, I'm going to sweep all the values from 1 to 10 and take a power reading at every one of those values. Well, I'm not going to in-queue check value 1, check value 2, check value 3, check value 4, check value 5 in terms of one list of actions. I'm going to go to a sweeping state and then say, do I have more things to do? Evaluate, do I have more things to do? If I have more things to do that small list of things and come back to that state and say, do I have more things to do? And at the end of all those states, I'll just increment my counter one, which offset I'm in my sweeping, and I will just work through that. So that is a reason why this is all part of the same loop, so that I can access that shift register. Now, could I put it in a global variable or a functional global variable or a DVR or some other mechanism? Sure, but there's other issues when you go that route. Yep. Oh, I'm getting the hook. All right.
The one problem with this, though, is that if I were to do that piece of code to anyone, by a developer, they have no clue what's going on without a 30-minute NJKirchner information session.
Well, luckily, there's yes.
It's not a fair critique, because there was a time when they couldn't have read a producer consumer. There was a time when they didn't know what a virtual instrument was. Any of our architectures requires a 30-minute NJKirchner intro. And I do require that we ship NJKirchner in all of our applications.
It is a basic functional reality.
But I agree. Probably, I agree with both. There's an antinomy with the whole thing. I agree with both, although they seem to conflict each other. The reality in this scenario is that I tried to take the least step forward and leaving as much sensible as possible, and I couldn't figure out any other way to add flow control to the program without going this route. There was one intermediate step that I had between this and something else, which is where I still had this section over here, but I would have a section of things here called like requests, or I would say I have trigger actions. And so everywhere else outside my program, I could in-queue a trigger action at any point in time, and it would now still be handled within here, which is still familiar, but it wasn't quite enough. There were too many implicit things that you had to do in order to not still step on your own foot. This one makes it a little bit more explicit in that fashion. Yep.
There's one piece I'm not totally understanding here.
Probably a few.
Yeah, so, can you in-queue multiple triggers when you're transitioning between states?
You can in-queue a trigger whenever your heart desires.
So here's, I guess, my concern.
Triggers can have different behavior.
Based on what state that you're in.
Based on the state.
And if you are in-queuing multiple triggers while in a certain state, you're going to only execute the state transition on the first trigger, my understanding, and then the following triggers may get executed on a different state after the transition happens.
Yep, potentially. But here's a scenario. I hit the exit button, then I hit the save button. Do I really care about that save button that I just clicked as I'm shutting my program down?
Right. So, I feel like.
But here's another.
Those transitions should be very, very fast.
Ideally, you want the transition.
And you should
you should block triggers when you're in a transition.
Speed
Right.
shouldn't matter.
Ideal.
This one I'll jump in on. If you're designing it based on speed, I guarantee there's a rate condition in your code.
Right.
So, don't care how long it takes. Trigger is raised, you're in a transition. Whatever
some
triggers
point in
fire
time.
during that transition, whatever additional triggers fire during that transition, you will handle based on already being in that next state.
Well, you'll handle the first one based on being in the next state, but that second one, if there's an additional state transition, that second one.
But you wanted that first, but here's the challenge though, you wanted that first trigger to happen. You wanted that first trigger to be handled. That first trigger took you to some place. So any trigger that you do after that point, you inherently want the program to respond to after you've done that first one. That ends up being the inherent challenge with that. And that was the problem with your traditional queued message handler, is you might be queuing into the queue
Well, yeah,
before you have actually a chance to go ahead and do the rest of it.
but I still feel like there's another, potential,
In this case,
race type issue that.
the closest you'll get to a race condition is you will end up in like a cycle that you didn't expect yourself to end up in. But you will safely be in that cycle. Potentially. Maybe.
There will be a provable followable path.
Yes.
There it is.
The bug, you will not end up in Heisenberg Central. You will end up in, well, that's actually what I did with the original program where it's like, this guy here.
You may object to the road you're on, but you will recognize you were on a road.
I was at least watching, this is cool. Actually, I should just let the program run. Come on, wake up. So if I go ahead and do this, I'm currently in the idle state. That's my action queue. And I can in-queue a trigger at the other side. I don't think I handled this stuff. There's two versions of this one. I don't have the right one loaded up. My apologies, or maybe I was. I could. Yeah. You have a rude question?
The word state
Cupcake?
delivery, I usually when I'm documenting or designing, state, the kind of state. So the state model that I use for UI is a behavioral model. Define the behavior of all the input and output channels right now. So I may be in a behavioral mode where I'm only allowed to display. I may be in a network disconnected behavioral mode where you can't do anything with all this packet. So are you implementing behavioral state in that sense, or are you implementing, what if I wanted to use this thing to control when the start button's enabled? What do you call state?
Yes, I'm glad you asked that one. So,
Because that's the visual state and the
Oh.
behavioral state of the button, and they're sort of blended together into what I would call just generally the behavioral state.
yes. So there's this question about state behavior. Is it a model-based behavior almost, or
State is such a slippery word,
Yes.
I'm asking you more explicitly to define what is state or thing.
a mode of your program? That's why I said, for me, they're almost analogous. They're practically analogous. If you can define your program being in a mode, that is a state for me. That is the very first way that I would evaluate. If you give me your program and you're like, I want to transition to this norm, what do? I would watch your program run. I would look at not only the visual cues, but its behavioral cues as well, and then I would start saying, that's probably a state right there. Let's talk more about what's happening. And the other part that I missed on the presentation is that something that is interesting. This is not a good example. Let me open up a more fleshed out example. Is it fleshed or flushed? I always forget. Anyway. Okay.
Well, one thing you can do is, right?
Fleshed. So here is a program that is more about taking measurements, that has like a connect and disconnect and start and stop. Once again, same base template. But the thing that's in particular I wanted to mention. Yep. Okay. People want to go home to their wife and kids. All right.
I'm good with staying late, but
Okay.
have some sort of, we can loiter after, but
Yeah,
you have a stake in the ground.
Yes, so I'll finish this out, and then we'll eat steak.
Kind of like an
So,
end state.
what's that?
Yeah,
This,
and please
an end
transition.
state.
Please transition.
Yes, this is fantastic. This is actually what happens at the end of the transition. At the end of a given transition, this is always what is called. If you remember over to this right part of the program, I always tag this guy down here. You can look at the logic, you can figure it out, but the basic idea is at the end of your logic, you declare where you're going. So I'm going to define my transition. I'm going to go to this state of the other side, to which I call the action change state, in which you now have the prerogative to go ahead and behaviorally set at least the visual aspect of your program to be like, well, I am now in this state. If I'm in this mode of the program, then I should probably set up my user interface to do very specific things. This is part of that functional Play-Doh where I'm saying, now I'm giving a home very explicitly to where I'm going to set up my UI to look like the mode that I'm actually in. And should it wait? Okay. So I will stick around to continue to babble on about this, but thank you everybody on the phone. If you've stuck around, I'm here.
Yeah, I wanted to just put a stake in the ground in case you want to leave. I personally don't think there's any problem with wanting to go over time and ask more questions. Probably 4 minutes.
Okay, is there any, business-related material to the meeting that you need to talk about?
Non-NI people. Non-NI people. Would you be interested in taking a 2.5-day active framework course for NI?
Yes.
Okay. Anybody else? Go ahead. One person?
Why right in front of me?
Because I've got customers who want to come in from out of town and take it. And so I'm trying to
Take your customers.
Say what?
They'll take your customers.
Not this one.
When you're done.
What kind of level are you talking about?
It'll go, it starts with a crawl.
If one hasn't been using it for almost the beginning.
What would probably,
Come on the last day.
In order to teach other people about it,
let's talk. I'm just wondering who to send the invitation to, essentially.
feel free to stand up. You want to hurt my feelings? Anybody want to talk more? I'm here.
And I may actually, if I have
Yes, Daniel.
If I don't like the implementation, where would I go to change?
No, I actually do have a question. Why would you, make, why don't in here?
Well, I don't like the idea of making the sub VIs that are going to take that massive cluster in. And if not that massive